this video is look at a shorthand representation to avoid us having to draw those beakers out all the time when we've set up a cell. So the IUPAC convention to represent cell diagrams without having to draw pictures of beakers obey the following rules. We've got some little rules we need to set out first of all. A vertical solid line in this diagram is going to indicate a phase boundary. Remember that phases are things like solid, liquid, gas. So if we change phase, so if our two chemicals have got different state symbols, we're going to draw a solid vertical line between them. A double vertical line in the middle of this representation is the salt bridge. So where we've got the salt bridge, we're going to have a double vertical line. That's going to look like this, just two vertical lines. That's a single vertical line. Other things we need to know is that the species, so we've got the species with the what for each half cell is written next to the salt bridge. So we're going to have something written next to the salt bridge. And it's the species with the highest oxidation state. It's going to be written, it's a bit of a lot to fit in. Highest oxidation state for each half cell is written next to the salt bridge. So out of copper and copper 2+, copper 2+ would be nearest to the salt bridge. Out of hydrogen gas and hydrogen ions would be nearest to the salt bridge. And then when measuring the standard electrode potential for a half cell, the standard hydrogen half cell is always shown on the left. So when we're doing a standard electrode potential for a half cell, and we've got the hydrogen one there, that's always going to be on the left. When we do any other electrochemical cell, so if you think back to the first video where we had the zinc and copper cell, any other cell, the positive electrode is going to be on the right, because at the positive electrode reduction occurs, and that's going to be on the right hand side, and the negative electrode is going to be on the left. These are some standard conventions that we need to learn and use. So let's have a think about how that is put into place for the copper half cell. So we were measuring the cell potential of the copper half cell. So because we were measuring it against the standard hydrogen electrode, we've got the standard hydrogen electrode on the left. We've got our vertical line representing a phase boundary. So why is that first vertical line there? Well, platinum is a solid and hydrogen is a gas, so they're in a different phase. We've got another phase boundary here because hydrogen gas and hydrogen ions are in different phases. We've got a salt bridge in the middle, and then we've got a final phase boundary between solid copper and aqueous copper ions. Another thing to bear in mind is imagining where the wire goes. Remember that the ions are flowing across the salt bridge in the middle, but your crocodile clips and your wire are going to connect the outside edges to the voltmeter. So the two things at the very extremes of this representation need to be solid metals to which you can attach crocodile clips. So when you finish writing it, if you've forgotten the platinum maybe, you need to remember that they're going to be there, got to be solid metals for the crocodile clips to attach to. So what we're saying here is that hydrogen is going to lose electrons to become hydrogen ions, and then copper 2+ ions are going to gain electrons to become copper metal. And then to work out the value for the standard electrode potential, you're just going to do the right hand side minus the left hand side. And since in this case the value for the right hand side in the tables is 0.34 and the value for the left hand side is 0 by definition because it's hydrogen, then the E0, the electrode potential for this cell, is going to be 0.34. This is writing a conventional representation, and we're going to be practicing this on the previous work in the next few videos.